module in this massive open online course. So, today let us start looking at the concept of a complex envelope and a complex pre-envelope of a signal. Okay. So, we want to look at the complex envelope, but to understand that first we have to understand the concept of a complex pre-envelope. So, towards this, consider a passband signal. So, consider a passband signal x t consider a passband signal x t, give it Fourier transform x f. So, naturally a passband signal has a Fourier transform that is centered around a carrier frequency f c. So, let us start by considering a passband signal x f, a passband signal x t, which has Fourier transform that is centered around the carrier frequency that is f c. Okay. So, I am drawing the spectrum of this passband signal which is centered at carrier frequency f c. So, let us say this is the spectrum x f. Okay, we have x t is the passband signal, it has for spectrum x f. So, your x t, this is basically the it is basically a passband signal in the sense that it has been modulated by a carrier. Therefore, its spectrum is centered at the carrier frequency that is at f c and at minus f c. Since it is a real signal, it is symmetric, correct. So, it has spectral band, it has basically two bands, one centered at f c and one centered at minus f c. Now, consider the signal, consider now we form a new signal . Now, the new signal x t plus j x hat of t, where x hat of t we know this is the Hilbert transform of x t. X hat of t is the Hilbert transform of x t. Is the Hilbert transform of x t. Okay. So, we are now forming a new signal which is x t plus j x hat of t, where x hat of t is the Hilbert transform of x t. We have already seen the concept of Hilbert transform. Therefore, the spectrum of this signal x f will be j x f plus j times spectrum of x hat of t, which is x f. So, this is the spectrum of this. So, its spectrum or Fourier transform of this signal x t plus j x hat of t will be x f plus j x hat of f. We have already drawn x f, that is the spectrum of x t. Let us now see what is the spectrum x hat f going. What is the spectrum of x f plus j x hat f. To do that, first let us start with x hat of f. Now, we know x hat of f is the Hilbert transform, spectrum of the Hilbert transform. This is equal to basically minus j sin f minus j sin f times x f. Now, minus j sin f is minus j if f is greater than 0 and plus j if f is less than 0. Let us draw the spectrum x hat f, which means it is minus j. So, x hat of f is minus j sin f times x f, correct. So, which means the positive band at f c is multiplied by minus j, this is minus j sin f, and the negative band, that is if you look at this band which is at minus f c, this band will be multiplied by j, correct. So, since this is minus j sin f, so this band will be multiplied by j. So, this is x spectrum x hat of f, spectrum of x hat of t, which is minus j sin f times x of f. Now, j times x hat of f, if we consider j times x hat of f, that is going to be multiply the spectrum of x hat of f by j, which means the positive side band, which is already multiplied by minus j, will be multiplied by, that will be multiplied by j. So, minus j into j, that will give a scaling of basically 1. So, this will give a scaling of 1, this is at your carrier frequency f c, and this is at carrier frequency minus c. It is multiplied by the negative side, negative band is multiplied by j, multiply that by another j, that is j x hat of f, that will give j times j, which is minus 1. So, this is the spectrum of j, this is basically j x hat of f, where x hat of f is a spectrum of x hat of t, okay. Or you can say this is a spectrum of j x hat of t. J x hat of f is a spectrum of j x hat of t. Now, the spectrum of x t plus j x hat of t. So, let us say we call this spectrum 1, that is spectrum of x t spectrum 1. This is basically your spectrum of x t, this is spectrum 1, and this is let us say spectrum 2, spectrum of j x hat of t. This is spectrum 2, okay. This is, so we have spectrum 1 and we have spectrum 2, all right. And now we have to find the spectrum of x t plus j x hat of t. J x hat of t, naturally that will be spectrum of x t plus spectrum of j x hat of t. Spectrum of x t plus spectrum of j x hat of t, which is basically equal to spectrum 1 plus the spectrum 1, which is spectrum of x t plus spectrum of j x hat of t, which is spectrum 2. So, what we have derived is we are trying to find the spectrum of x t plus j x hat of t. We have derived the spectrum of x t, we have derived the spectrum j x hat of t. We are now trying to add these two spectra, and when you add these you can see that here if you look at the spectrum of x t, now spectrum of x t is simply both the side bands scaled by 1, that is unity factor, that is the default. Now, if you look at the spectrum of j x hat of t, you can see that the positive band, the band that is at f c is scaled by 1, the band at minus f c, that is the negative band, the negative frequency band is scaled by minus 1. So, when you add these two, the positive frequency band, that is the frequency bands corresponding to the positive frequencies will add. So, you will have a net scaling factor of 2, and the frequency bands corresponding to negative frequency will cancel out each other, that is 1 plus or minus 1 0. So, what you will have is net scaling factor 2 for the frequency band corresponding to the positive frequency and scaling factor 0 for the frequency band corresponding to the negative frequency. And therefore, what you will have the spectrum, and now it is easy to speak, spectrum of x t plus j x hat of t equals x f plus j x hat of f, and we already found this x f and j x hat of f. Now, when you add these in the positive frequency, what you will have is you will have a scaling by a factor. So, this is f c, the positive band is scaled by a factor of 2, the negative band is simply scaled by a factor of 0. So, basically you will have nothing. So, basically all you will have, this is equal to, now you can see this is equal to twice x f for f greater than 0, 0 for f less than 0. So, x t plus j times x hat of t has the spectrum x f plus j x hat of f, which is basically the positive bands, that is the bands corresponding to frequencies greater than 0, these add up. So, you will have a scaling factor of 2 corresponding to the band of positive frequencies, correct, and the negative frequency, the bands in the negative frequencies they cancel, and therefore, you have a scaling factor 0. So, basically it is twice the original spectrum of x f, twice the original spectrum of x f for f greater than 0, that is for the positive frequencies, and it is 0 for f less than 0, and this is known as the complex pre-envelope of the passband signal x t. So, this basically x t plus j x hat of t, which basically has the spectrum, twice x f for f greater than 0, 0 for f less than 0. This signal is termed as the complex pre-envelope, the complex pre-envelope of x t. This signal is termed as the complex pre-envelope of x t. That is, we consider only the positive frequency band and scale it by a factor. The negative frequency band is set to 0. Consider the positive frequency band in x t, scale it by a factor 2. Negative frequency band is set to 0. That is basically, to describe it simply, positive frequency band in x t or x t or f x f, x f scaled by 2 and negative frequency band set to 0. This is known as the complex pre-envelope. Now, you can see that this complex pre-envelope has only a band at Fc. If I shift it by minus Fc, that is, it is at Fc, centered at Fc, if I shift it by minus Fc, that is shifted to the left by Fc, it will be centered at 0. So, that will give me a baseband signal, but it will be a complex baseband signal, alright. So, if I take this and let me draw it in a separate figure. This is my complex pre-envelope, sideband scaled by a factor of 2. If I take this and shift this by minus Fc, so let me draw this by to shift it so this is basically shift by minus Fc or Fc to the left. This will be a complex baseband spectrum. This will be a spectrum of a complex baseband signal. And remember, shifting by minus Fc or shifting by Fc to the left is nothing but using the modulation property, it is basically multiplying by e to the power of minus j 2 pi Fct. So, if I take this complex pre-envelope x t multiplied by e to the power of minus j 2 pi Fct, I will get a complex, I will get a baseband signal or complex baseband signal. This is known as the complex baseband equivalent of the passband signal x t. So, basically now if I look at this complex pre-envelope, and multiply it, modulate it with e to the power of minus j 2 pi Fct, this signal has a spectrum, this shifts the spectrum to the this shifts the spectrum to the baseband, that is around 0 frequency. Shifts the spectrum to around 0 frequency. This is termed as the complex baseband equivalent. Also, this is a complex baseband signal. So, this is a complex baseband signal, this is a complex baseband signal, this is termed as the complex baseband equivalent of the passband signal x t. Complex baseband equivalent signal of complex baseband equivalent signal of the passband, complex baseband equivalent signal of the passband signal x t, that is, and this is denoted by x tilde t. And you can see we have already shown this as a spectrum, that is, you take the positive frequency band of x t scaled by a factor of 2, shift it to the 0 frequency, that is shifted by Fc to the left. Okay. So, the spectrum of the complex baseband equivalent signal is simply the positive frequency band of x scaled by a factor of 2. So, therefore, this point will be twice x of f c, that is the original spectrum x which is at f c, that scaled by a factor of x at point f c scaled by a factor of 2. So, this is basically at this point at the 0 frequency, and this is basically what we are saying is this is your x tilde f, this is x tilde f. So, this is x tilde f, which is spectrum of x tilde t, or the complex baseband equivalent signal of x t. So, this is spectrum of x tilde t, and it is worth noting again that x tilde. So, what is, so we are taking this passband signal x t, and we have demonstrated that this passband signal, any passband signal x t can be reduced to an equivalent baseband signal, a complex baseband signal. This complex baseband complex baseband equivalent signal is denoted by x tilde t, which is given as x t plus j x hat of t times e to the power of minus j 2 pi f c t. So, x tilde t is the complex baseband equivalent of the passband signal x t. Okay. And it has a spectrum which is the spectrum, the positive sideband, the sideband correspond, the band corresponding to the positive frequencies shifted to the 0 frequency and scaled by a factor of 2. Further, also note that this x tilde t is also known as the complex envelope of x t. It is a complex baseband equivalent. It is also known as the complex envelope of x t. This is also another term. This is also known as the. So, we have seen the complex pre-envelope, that is x t plus j times x hat of t. If you multiply that by e to the power of minus j 2 pi f c t, where f c is a carrier frequency, we will get the complex envelope, that is shift it to 0 frequency, you will get the complex envelope, also the complex baseband equivalent of x t. Okay. So, the x tilde t is the complex envelope. Okay. And why is this known as the complex envelope? That is, if you can look at this, let us look at this, observe that if you consider the real part of x tilde t e to the power of j 2 pi f c t, that will be the real part of, now x tilde t is x t plus j x hat of t into e to the power of j 2 pi f c t into e to the power of minus j into e to the power of minus j 2 pi f c t x t plus j x hat t into e to the power of minus j 2 pi f c t into e to the power of j 2 pi f c t, this e to the power of minus j 2 pi f c t, e to the power of j 2 pi f c t, these cancel. So, I am left with the real part of x t plus j x hat of t, and the real part of x t plus j x hat of t is simply x t, which is your original passband signal, and this is the original passband signal. Therefore, one can write the passband signal x t as x t equals real part of x t plus or real part of x tilde t e to the power of j 2 pi f c t. So, this is x tilde t is the envelope of e to the power, because if you look at magnitude of this quantity x tilde t e to the power of j 2 pi f c t, that is magnitude x tilde t. So, this is acting as the amplitude of e to the power of j 2 pi f c t, or this is basically the complex envelope of the signal x tilde t e to the power of j 2 pi f c t, okay, and real part of that is basically your passband signal. So, if you look at it, the passband signal x t is nothing but real part of x tilde t e to the power of into e to the power of j 2 pi f c t. So, you can see it is as if there is this exponent, that is sinusoid e to the power of j 2 pi f c t with a complex envelope x tilde t. Therefore, x tilde t is known as the complex envelope of this passband signal x t. Okay, so, it is as if it is acting, it is an envelope. Strictly speaking, it is not an envelope, because the envelope is simply the amplitude of the sinusoid. Therefore, this is a complex envelope x tilde t into e to the power of j 2 pi f c t. It is, it can be seen, it is as if the amplitude of this sinusoid, complex sinusoid, is modulated by this complex envelope x tilde t. Therefore, x t is the passband signal, x tilde t is its complex envelope, or also its complex baseband equivalent, because it has a spectrum which is in the baseband. Okay. So, this is the complex envelope of the signal x t, x tilde t is a complex envelope, and x t is your passband signal. X t is the passband signal, x tilde t is the complex envelope or the complex. So, x t is the passband signal, x tilde t is the complex envelope or the complex baseband equivalent of the passband signal x t. And therefore, we can see that every complex, this is an important principle of in communication, that is every passband signal x t can be reduced to an equivalent complex baseband signal x tilde t. And this is very useful for the analysis of communication systems, because now what this says is all the analysis of communication systems can be carried out in the baseband by establishing an equivalence to this complex baseband signal. So, one can remove the effect, or not remove the effect of carrier frequency, or rather basically normalize it, so that all the analysis can be carried out in the baseband for all the signals irrespective of the carrier frequency f c, that is a unified framework can be developed for the analysis of all these communication systems in the baseband by reducing these passband signals to the equivalent complex baseband signals. Alright. So, that is another, that is the use of the Hilbert transform. So, where we use the Hilbert transform x hat of t of x t to construct first the complex pre-envelope as x t plus j x hat of t, and then shift the resulting spectrum to the baseband to derive the complex envelope or the complex baseband signal corresponding to x t. Alright. So, this is the principle of the complex envelope of a passband signal x t. We will stop here and continue in the subsequent modules. Thank you.